So there's a certain amount of carbon that is circulating through the environment. So it's going into the air, being absorbed by, and then getting absorbed by plants and animals, and then going back into the air. And this carbon is just circulating on the surface. And this is fine, and it's been doing that for millions, hundreds of millions of years. The thing that's changed is that we've added something to the mix. So this is what I would call the sort of the turd in the punch bowl. So we added all this extra carbon to the carbon cycle, and the net result is that the carbon in the ocean's atmosphere is growing over time. It's much more than can be absorbed by the ecosystem. It's really quite simple. We're taking billions of tons of carbon that's been buried for hundreds of millions of years and is not part of the carbon cycle, taking it from deep underground and adding it to the carbon cycle. The result is that a steady increase in the carbon in the atmosphere and in the oceans, which doesn't look like much if you look at it on this chart, but when looked at in the context of history, it actually looks like this. So the carbon parts per million has really been bouncing around the 300 level for around 10 million years. And then in the last few hundred years, it went into a vertical climb. This is the essence of the problem. This is very unusual.
Being called the breakthrough of the century. Scientists confirmed Thursday gravitational waves exist. Albert Einstein first explained them in his general theory of relativity a century ago.
We had two black holes over 1 billion light years from Earth, each one weighing about 30 times the mass of our sun, that collided, and the shock waves took over 1 billion years, and they finally reached the planet Earth, vindicating Einstein's theory of gravity.
These gravitational waves have been traveling through the universe for over 1 billion years until they passed through the Earth on September 14th. And these waves are ripples in the fabric of space-time itself, and LIGO is an incredibly sensitive machine that measures these tiny, tiny ripples, allows us to extract these ripples in space-time, and using those we can do astronomy and physics and make these amazing discoveries. So if you think about ripples on the surface of a pond, imagine you can't see the pond. What you could do is you could float 2 corks on the surface of the pond, and as the ripples go past on the surface, the corks will bob backwards and forwards. And if you can measure the distance between the corks, you can see the effect of the ripples, even though you can't see the ripples themselves. And LIGO uses lasers and very, very precise measuring equipment to measure the distance between 2 mirrors that are a distance of 2.5 miles apart. And as the gravitational waves go past, they cause these mirrors to ripple backwards and forwards, a distance small, about 1,000 times smaller than the diameter of a proton. And by measuring these tiny, tiny ripples, we can extract the information from the waves. The thing we're extracting really is the information, the waves, the existence of these waves, and we can use the information carried in these waves to tell us about the sources that generated them billions of light years across the other side of the universe.
That's amazing.
Remember that we have light telescopes given to us by Galileo. During World War II, we got radio telescopes that allow us to see galaxies far away. Now, this could usher in the third type of telescope. That is gravity wave telescopes on the Earth and also in outer space.
So we've got lots of distant galaxies. We know how far they are away. We know how fast they're receding. What we find is something called the Hubble law. And it's basically very simple. It says that the further a galaxy is away, the faster it's flying away from us. Now, how are we to interpret that? I mean, you might naively say, well, does that mean we're somehow at the centre of the universe and everything's flying away? Well, no, actually. If you think a little bit more, if you think, for example, about baking bread, if you get a lump of dough and put raisins in it and stick it in the oven, then the bread expands. So all the raisins move away from every other raisin. If you were sat on one raisin, what you would see is the Hubble law, exactly the Hubble law. You'd see the ones close to you moving away more slowly, the ones further away moving away quicker, because the bread is all stretching. All of space is stretching at a constant rate.
You don't have to go back very far, only about 100,000 years, and all our ancestors lived in Africa, were African, and walked out of Africa not that long ago. So we are African, actually we're African apes. We're all African apes, and somehow brings us all together, don't you think?
We're apes with a shave.
It's not just that it suggests that she thinks that monkeys turn into humans overnight, but
Right.
it's also the fact that monkeys are very good doing what they do. They live up trees, and it's a very good thing to be a monkey if you're up a tree. You might as well say, why aren't humans turning into monkeys? Because we have a common ancestor with monkeys, which lived
Right.
about 20 million years ago, and we've both been evolving ever since. That's as simple as that. Most of evolution happened before we were born and took much too long for us to see, but there are just a few examples, and these lizards is one. They were moved from one island in the Mediterranean to another, and within a couple of decades, they had evolved a completely new diet, and that had changed their jaws, even changed their stomachs, and they now got stomach valves. In just a couple of decades, just think what could be achieved in 1,000,000 years, 100 million years.
The fact that pie, right?
Let's say the numbers together. 3.1415926.
We got a few
That's
geeks over
pretty
there.
good. That's a nerd fest.
We got a geek thing going on over there. I
Not
felt.
bad, not bad.
The fact that you take a circle of any size, a circle the size of the universe itself, and divide it by its own radius, and you get that number, that's beautiful. I have to pause, and I get misty thinking of this. I'm sorry, that's just another one, that the atoms and molecules in your body are traceable to the crucibles in the centers of stars that manufactured these elements over its lifespan. When unstable, on death, exploding its enriched guts across the galaxy, scattering it into gas clouds that would ultimately collapse and make a star and have the right ingredients to make planets and people. Which means we are part of this universe. As I've said many times, and goes back, not only are we in the universe is in us. That is a profound concept. And I think it's the greatest gift that astrophysics gave culture in the 20th century.
Global warming, the greenhouse effect. You put gases like carbon dioxide or CFCs, other greenhouse gases, into the atmosphere over this country. They don't stay over that country. Those molecules don't have passports. They don't know about national sovereignty. That's something they never heard of. The atmospheric circulation spreads those gases all over the planet. And so what one country does affects all the other countries. The solution to these kinds of problems has to be that everybody on Earth works together. The industrialized nations have the biggest responsibility because they're the biggest polluters. The United States puts more CO2 in the atmosphere than any other nation. But Western Europe and the Soviet Union and Japan and even the developing countries all make significant contributions. So there has to be a new way of looking at the future, and that is that we're all humans, members of the same species, on one fragile little planet. We're all in this together, and we have to work together. That's kind of the silver lining of these crises. They are forcing us to become a planetary species.
The fastest hunk of hardware we have ever launched is the mission to Pluto right now, the New Horizons mission. It's going at like 4 times the escape velocity from Earth, and it's going to leave the solar system after it swings by Pluto. It'll get to Pluto faster than any spacecraft ever would have gone that distance. It's a tiny spacecraft on the largest engines in our arsenal. You combine those two facts, laws of physics say this thing is going to be hauling, okay? It's going to get to Pluto by 2015. If you hitched a ride on that, it's the fastest thing we've ever launched. If you just grabbed on and didn't worry about food or want to come back or anything like that, at that speed, you would reach the nearest stars in about 35,000 years. So, we are hopelessly bound to the solar system in this regard. The distances between stars is vast. We would need to understand something new about the fabric of the space-time continuum and exploit that in order to expect to travel to the stars.
Did you know that in 1801, the Planet Ceres was discovered? Did you know this? Planet Ceres. You ever hear Planet Ceres?
If you're an astrologer, you have.
Astrologers know about this?
Oh, yeah, they've got series and charts. I was going to ask you about that. Why aren't the astrologers engaged?
Oh, they are. So
Whether or not
astrologers were
Pluto-
as pissed off as the third graders that Pluto got demoted. So 1801, planet Ceres was discovered. Everybody was excited. And then a couple of years, within a few years, 3 more planets were discovered in orbit around the sun between Mars and Jupiter. Because there was a big gap there that was not understood for a long while. And so if you have books in the early 1800s, the planet, and they discovered a bunch of these, the planet count was up to 13 for a while. Did you know that? 200 years ago, 13 planets. And then people said, no, wait a minute. These objects are kind of small. In fact, they're really, really small. And they're like, there's tons of them. And they're all kind of in the same orbital zone. They have properties that are not like these other objects we've been calling planets. And so it took 50 years, but in the early 1850s, it was widely decided that maybe we were not discovering planets, we were discovering new objects, a new kind of object, in a new swath of real estate in the solar system, which then became known as the asteroid belt.
Einstein went on from thinking about moving clocks to thinking about what happens to time and space in the presence of heavy things like planets and stars. And he found, or his theoretical prediction was, that not only does movement bend space and time, but heavy things like planets and stars bend space and time as well. And he made predictions about what that means. It actually means that when you're traveling through space near a planet, you feel like you feel a force, because you're moving through bent and curved space and time. That force is gravity. It's a beautifully elegant theory. In fact, I even wrote that down. That's Einstein's theory of general relativity. The whole theory of gravity, the best theory of gravity we have, in one line. Actually, this thing here just tells you how the mass of a planet or a star is distributed, and this thing here tells you how space and time curve. That's it. That's all there is to it. And then the picture is that as things move through this curved space, they bend because they're going through a curved space, and that's what we feel as the force of gravity.
If there was no concept of having stewardship of the Earth a million years ago, today there is at least a very great need. If you stand back from the Earth, as those Apollo astronauts did in the late 60s, and photograph the Earth from a distance in space so you can see the whole Earth, there's this blue aura that you can see surrounding the daylit hemisphere. And it's just the atmosphere seen edge on. And what is most impressive, what many astronauts have remarked upon, is how thin, how fragile, how vulnerable it seems. The thickness of the Earth's atmosphere compared to the size of the Earth is about the same as the thickness of a coat of shellac on a library globe of the Earth. There isn't much air. And so we now have the prospect of inadvertently endangering the life-supporting environment, the environment that supports the human species, and many other species, of committing what religious people sometimes call crimes against creation.
Now, I want to say there is a historical perspective which suggests, as bad as our problems are, the nuclear arms race, the environmental issues, as bad as all that is, there is some reason for hope. There was once slavery on the planet. It is largely gone. There was once human sacrifice. There was once the divine right of kings. There was lots of stuff that today we consider...
Oppression of women.
Absolutely. I'm sorry I didn't say that. All of that is changing. And we can change these issues too, because our lives depend on it. We're smart enough, we're dedicated enough to do it, but not by sitting on our duffs. We have to really work. Another aspect that I think is tremendously important is those photographs of the Earth alone in space, fragile, blue world, in this vast blackness, this vacuum, velvety vacuum of space. And it's clear, it's very thin atmosphere. It's so sensitive to the depredations of human beings. You look at that and you say, hey, that's only one little world. We don't have anywhere else to go. No other planet in the solar system is a suitable home for human beings. It's this world or nothing. That's a very powerful perception. Then, in the particular field that I'm involved with, the exploration of planets, usually by robotic spacecraft, there we have opened up a universe of wonders. We have looked close up at dozens of new worlds, worlds that we never saw before. And unless we're so stupid as to destroy ourselves, there are going to be people exploring those worlds. There are going to be human habitations on those worlds. We're going to be moving out into space in the next century. And I'm fortunate enough to have played a role in the first preliminary reconnaissance of the solar system. That's a terrifically exciting thing.